Okay, we are on to Chapter 5 now, Systems of Equations and Inequalities. Let's go over a little bit of terminology here, and then we're going to go over the general idea of what's going to happen within each section here, just to make sure that we have an understanding of where we're going. First of all, systems, in this case, just actually means more than one. So basically, we're going to have more than one equation or inequality on the same graph. And what do I mean by that? Well, it basically means something like this. If I have, and I'm just going to do a couple of linear ones here, but it could be anything. If we were to have something that looked like this, I might have a line that does this. That's one equation, whatever that is, that's going to be some equation, but then I could also have a different graph which does something like that. And they don't have to be linear, it's just got to be more than one equation. You could have a parabola, or we could have a cubic function and on a line. It could be anything where you've got more than one equation on the graph. That's the idea behind systems of equations. The general idea is we are trying to find where the two or more graphs intersect. Now, we're only going to be dealing with two in this class. We're not going to be dealing with more than two. But we're trying to find the intersection. So in this case, it should be very clear that right there is the intersection of those two. Whatever that ordered pair is right there, that's going to be the solution to our equation. Alright, so today we're going to start 5.1, which is just going to be systems of linear equations. Okay, section 5.1 is systems of linear equations in two variables. Believe it or not, you can have systems of linear equations in 3 variables, 4 variables, and actually you can have an infinite number of variables. We're only going to be dealing with 2. So for the most part, we're going to be dealing with things that are typically going to be x and y, because we're usually going to be using the x and y coordinate axis, the one that we're used to doing, so we can plot points. So to start, there are 3 possibilities. There's really only 3 ways that this can happen. I could have, and I'm going to draw 3 different little xy planes here, just so that you can see. These are all xy. Oops. Xy, and then xy. So there's really 3 possibilities, 3 things that could happen. If I've got linear, first of all, linear equations just means lines. So all we're dealing with in 5.1 is lines. I could have an equation that the first line does something like this. Okay, and then I could have something else where, as long as the slope of the second line is different than the first one, it's going to intersect the second one somewhere. So this one, you can clearly see, intersects. This has one solution. There are no other places these lines could ever cross, because of the fact that they go on forever in the same direction that the arrows are pointing. They will never come back around and touch each other anyplace else. So in this case, there is one solution. So I could have one solution. I could also have a possibility of, maybe I've got a line that does that, and then the second line does that. Assuming that I've drawn this correctly, and assuming that these two things are parallel, they will never touch. There will never be any point that on this graph where these two things intersect, so there would actually be no solution to this. Okay, and that's the second possibility. The third possibility is kind of a little bit strange to think about. I could have a line, and then the equation of the other line that I have on my graph, it may not look exactly the same. We could probably manipulate it to get there, but it could actually be something where it falls exactly on the same line. So these two things would actually be exactly the same equation. It just might not look that way when you start off. If that's the case, because every single possible point on both lines intersects with every possible point on the other line, you have an infinite number of solutions. So those are really the three possibilities. I could have one solution where the two lines cross each other. I have no solutions because they're parallel and they'll never touch each other. Or I could have an infinite number of solutions because the lines actually lie right on top of each other. Those are the three possibilities for the system of linear equations in two variables. Okay, for our first example, we're going to just be given two equations. So we're going to write these, and we write the little brace. Oh, that was horrible. Let's try that again. We write the little brace notation, because that's just going to tell us that I've got more. Man, I am doing this awful. We've got more than one equation. There we go. That's a little better. So the first equation is going to be x plus 2y equals 2. The second equation is going to be x minus 2y equals 6. And all we are being asked to do here, we're not actually being asked to solve this one. All we're being asked to do here is we're going to be asked to determine if a given point is a solution to this system of equations. So I'm going to give you a point. I'm going to say that we're going to try the point 4, -1. And we're also going to try the point -4, 3. For this point, or either one of these 2 points, to be a solution, it has to satisfy both equations. It can't satisfy one. It definitely can't satisfy neither one of them. What you basically have to do is you have to take the x and the y and plug them into each one of the equations and see if each statement is true. So let's go ahead and try that. Let's try letter A. If we take x is 4 and y is -1 and we plug it into the top equation, we're going to get 4 plus 2 times -1 equals 2. And let's simplify that and see if that works. So we get 4 plus -2 equals 2, and 4 plus 2 is 2, so the first one works. Okay, that satisfies the top equation, so that one worked out. Let's try the bottom equation because it's got to satisfy both of them. So let's go ahead and plug 4, -1 into the bottom equation. So we would get 4 minus 2 times -1 equals 6. Okay, so that would be 4, -2 times -1 becomes plus 2 equals 6, then of course 6 equals 6. So it satisfies that second equation as well. So this is a solution. That works. Let's try the second point. So if I was to take -4 and 3, plug it into the top equation. So we would get -4 for x plus 2 times 3 equals 2. So -4 plus 6 equals 2. So -4 and 6 is 2, so 2 equals 2. So that works. The second point works on the top equation. We have to try the bottom equation. It must satisfy both. So I'm going to take -4, plug it in for x, minus 2 times 3 has to equal 6. So we'll get -4. -2 times 3 is -6. Equals 6. On the left side here, now I get -4 minus 6, but that's -10. That is a false statement. So this one right here is not a solution. It does not work. The letter A did work. It satisfied both. Letter B only satisfied one of the two equations. Therefore, it is not a solution. Basically, that means these two linear equations do not intersect at -4, 3. And if you're really thinking about what we said before, since it did intersect at 4, -1, that is the only intersection point that it can have, because it can either only have one intersection point, no intersection points, or an infinite number of intersection points. Since this second point didn't work, most likely this is not going to be anything other than one intersection point.